Now let's look at one more example that involves negative components. First, the boat travels 55 meters in this direction, and then 50 meters in this direction. What is the magnitude and angle of the total displacement vector? The first vector, d1, has a magnitude of 55 meters, but this time it's at an angle of 15 degrees below the positive x-axis. Using the convention that we learned in a previous video, we would say it has an angle of negative 15 degrees because it's clockwise from the positive x-axis. This positive 15 degrees would be the reference angle. The second vector, d2, has a magnitude of 50 meters and an angle of 112 degrees. The reference angle would be 68 degrees between the vector and the x-axis. So what do the components look like? There's a lot of stuff overlapping each other in this example, so we're not going to look at everything at once, and we should probably keep track of the numbers on the side. This might look confusing, but everything works the same as before. d1 has x and y components, d2 has x and y components, and d total has x and y components. We're still going to add delta x1 plus delta x2 to get delta x total. And we still add delta y1 plus delta y2 to get delta y total. These might look confusing because they're in different directions, but we'll explain that as we work through the example. So first we need to find the components of d1 and d2. Let's start with d1. Now that we're dealing with negative components, there's two ways we can do this, which we talked about in a previous video. The first method is to use the reference angle between the vector and the x-axis, which is positive 15 degrees. The x component is still d times the cosine of this angle, so we plug in 55 meters for d and 15 degrees for theta, and we get 53.13 meters for delta x. Now we need to check if the component is positive or negative. Since it's pointing to the right in the positive x direction, delta x is positive 53.13 meters. The y component is 55 meters times the sine of 15 degrees, which is 14.24 meters. But we can see that the y component is pointing down in the negative y direction. So delta y is actually negative 14.24 meters. The other way we can do this is by using the conventional way of describing angles. We measure a vector's angle relative to the positive x-axis. Counterclockwise angles are positive and clockwise angles are negative. If it helps, you can draw the vector at the origin of the x and y axes to get a better picture of the angle between the vector and the positive x-axis. This vector is 15 degrees clockwise from the positive x-axis, so its angle would be negative 15 degrees. If we plug negative 15 degrees into the sine and cosine functions, then we still get positive 53.13 meters for delta x. But now the sine function gives us negative 14.24 meters for delta y. So if we use this method and plug in the conventional angle, the positive and negative components are taken care of. Let's save these values for later and find the components of the second vector, d2. This vector has an angle of 112 degrees, and the reference angle is 68 degrees. Let's use the 68 degrees first. The x component would be 50 meters times the cosine of 68 degrees, which is 18.73 meters. But the x component is pointing in the negative x direction, so delta x would be negative 18.73 meters. The y component is 50 meters times the sine of 68 degrees, which is 46.36 meters. That stays positive because the y component is pointing in the positive y direction. Now let's try using the conventional angle of 112 degrees counterclockwise from the positive x-axis. If we plug that in, now we get negative 18.73 meters for delta x, and positive 46.36 meters for delta y. So, those are the components of D2. Now we need to find the components of the total displacement vector. Delta x total equals delta x1 plus delta x2. Delta x1 is 53.13 meters, and delta x2 is negative 18.73 meters. That gives us 34.40 meters for delta x total. Notice how we're adding the two components, but delta x2 just happens to be a negative value, so the math is the same as 53.13 minus 18.73. When we add the components graphically, we start with delta x1, and then we add delta x2, which is negative, and points to the left. So the sum of the two components, delta x total, looks like this. The boat moves 53.13 meters to the right, then 18.73 meters to the left. So the overall displacement is 34.4 meters to the right. This is why we needed to keep track of negative components so the directions add together correctly. Drawing the vectors and components can help us see what's going on, but the numbers take care of things for us. We ended up with a positive 34.4 meters for delta x total, which is the correct value and direction. Now let's find the total y component. We plug in negative 14.24 meters for delta y1 and positive 46.36 meters for delta y2, which gives us 32.12 meters for delta y total. In the y direction, the boat moves down 14.24 meters, then up 46.36 meters, so its total displacement is 32.12 meters up in the positive y direction. Now we can find the magnitude and angle of the total displacement vector using the same equations as before. For the magnitude, we plug in 34.40 for delta x and 32.12 for delta y. And we get 47.06 meters for the magnitude. For the angle, we plug in the same values for delta y and delta x, and we get an angle of 43 degrees. So the total displacement of the boat is 47.06 meters at an angle of 43 degrees.